Salutations, Internet. Good time zone. So let's do some recap and housekeeping. We have here our brand new equations that we derived in the previous episode. If you want to see where I messed up in this equation, then I recommend checking out the previous video and you'll see it firsthand. If you already know how I messed up and how I addressed it, then you're all caught up to speed and we can carry on. So housekeeping now. To begin, I want to point out that this is a time position relationship for things in orbit, for hyperbolic trajectories. Ah, that's interesting. This equation set will not work for that. So we will spend some time. Let me double check my notes. I'm pretty sure we spend some time later on. And indeed we do spend some time later on deriving a time position relationship for those. Stay tuned for that. For right now, we're just going to carry on with this. Let's see. Right. The last point that I want to give before we move on is I thought that I was going to edit out more of last week's video than I actually ended up doing. As a result, the video is far longer than I had planned for. So to make up for it, I am going to do my best to make sure that the next few weeks are shorter and more digestible, more easily digestible. And with that all out of the way, I'm pretty sure that was all I wanted to share at least. Let's go ahead and dive into things. I want to take a moment to point out this in here, the square root of a cubed over mu. That's come up before over here in our periodicity equation. And both of these have to do with time. So one can reasonably assume that there is some connection to time with it. So I have the equation written up over here just so it's a little bit bigger. And let's take a look at the components. So we have a cubed, which is kilometers cubed. And we have as well mu, which is kilometers cubed over seconds squared. And in the context here of the square root of a cubed by mu, we have kilometers cubed by kilometers cubed over seconds squared. Kilometers will cancel out. That's going to leave us with the square root of seconds squared. Lo and behold, we're left with seconds. So, indeed, yes, there is a time element associated with that connection. And it was so prominent that Kepler spent a lot of time and energy to highlight that point in his works. So let's rewrite this equation, but with all the time elements on one side. So let's do this, mu over a cubed square rooted times t minus tp equals e minus e times the sine of e. Do that. All right. So in this context, we have radians over on this side. We have time here, and then we have what is now per second, because we just divided that over onto this side. That per second is actually going to end up being radians per second. Let me figure out how I want to do this. That is not blue. Now it's blue. this becomes radians per second, which is actually a rather important, I say rather important, it's an important enough term that we give it its own variable, n, and we will write that as square root of mu over a cubed. And I'm going to go ahead and box it before I tell you its proper name. This is the average angular speed. Average angular speed, n. So throughout an orbit, this is, on average, the speed that it goes. It's fairly self-explanatory. You know me by now. I like doing proofs of things. So let's take a look at our periodicity here. 2 pi radians to complete a full cycle times a cubed over mu square rooted. Well, that is the same thing as 2 pi over n, where we had n being radians per second. So now we have, well, I'll tell you what. We had radians up here. We have radians per second down here. Radians cancel. We're left with seconds. And that is how we like to describe our period. Excellent. It lives up to the hype that we've been giving it. You'll love to see it. Let's actually return back to here now. I did not need to scroll down. So we have a term of radians over here. We have a term of radians over here. And we can make this more compact by giving it its own definition, m. And I'm going to go ahead and write that down here. M is equal to the eccentric anomaly angle. Again, this is in radians, minus the eccentricity times the sine of the eccentric anomaly angle. And this can be radians or degrees, whatever. Just, again, make sure that you actually know which you're doing. And we'll get into that here in a little bit with the example. And that's a good idea to record and keep track of, I would say, I would argue. Just because it does make things a little bit easier when you have one term floating around as opposed to 3 terms in a trench coat. I told you this was going to be quicker. We're already going to get into our... oh my. We're going to get into our example for the video. So please stand by. Okay. So we're back. We are going to be using the same system that we have been using for most of the series. And we're going to look for the eccentric anomaly angle, the time it took to get to where we are from periapsis, and we're going to find out what the average angular speed of our entire orbit is, because why not? So let's go back to here. And this seems to be a good enough starting spot, at least in my opinion. So we know, once again, I have it written down here. We have from the center of our orbit to the focal point, plus the radius projected downward onto that, we'll call it the x-axis for now. That's going to be the same as the semi-major axis projected onto the x-axis. So let's go ahead and rewrite that equation. And you won't have to go back to an arbitrary equation like this later on in the series, because there are quite a few more equations to draw up here, and one of them is going to be easier to work with. However, we're going to go along with this one right now, because I think it makes more graphical, intuitive sense. It's easier to visualize. I'll say that. Centric anomaly. Cool. All right. So now that we've done that, let's solve for E. Divide by A. And then our cosine. And we'll do that. I'll give me some more room. I'll go down to here. There we go. And let's plug in our numbers. $20,000. I just realized I haven't been talking while I've been doing this. This is a first for me. That's the cosine of 30 degrees. All right. You plug that in, you're going to get a value of 24.68141866 degrees. But before you clear that value from your calculator, I want to remind you that we are going to be looking for time, and we do need it in radians. So let's go ahead and convert that to radians. And that will give us an eccentric anomaly value of 1.2384944791. Well, this is awkward. See, I got this first equation right. This first answer right. But the second one is very much wrong. Pro tip, if you are trying to convert an equation from degrees to radians, like I did here, make sure that all of your trig functions inside of that bigger function also adhere to the radians or degrees, whichever one you choose. So, as you can guess, I didn't do that. So let's remedy that, shall we? We'll start with what I did do right. I have a degree answer of 24.68 and change. There's a couple of ways that you can go about doing it. There's the longer, more roundabout way of calculating what this is, saving that value, plugging that value back in after you've converted this back to radians, and then Bob's your uncle, here's your answer. That is a perfectly fine way of doing it. Or you can take this answer, multiply it by pi divided by 180. And then there's your there's another way of getting to your answer. And because that's faster, I'm going to do that one. So let me plug this in over here. Bonus points to you if you manage to figure out that something was wrong before this edit came in. Good for you. So we want 0.430777202. Make that look like a better 2. There we go. Radians. Awesome. All right. Now we have a good value that we can plug into this equation right here. So let me try that again. A cubed by mu. I'm not going to bother rewriting this step because it's already written here. I will, however, rewrite this one. So give me just one moment. Square root, that bigger square root. A cubed by, I don't need to do that. I just said I wasn't going to do that. 20,000 cubed by mu 3.986 times 10 to the 5th. 0.4307702 minus 0.2 times the sine. It's the sine of, and for the sake of consistency, 30770. Nope. Too soon. 202. Do not write degrees there because that is not a degrees. It's going to give us a time value of 1,555 seconds. 0.71. And to put that into something that is more useful for us as humans, this is fine for computers, but for us as humans, it's going to be 0 hours, 5 minutes, 55.71 seconds. And if you were to do this with degrees, here instead, you ought to get the same answer. In fact, I will double check that now. Yep, just confirmed it. Should be good to go. And with that in mind, yes, that should be all that there is for this particular editor's note. Here we go. And finally, we take a look at our average angular speed, which is, as a reminder, mu by a cubed. That becomes 3.986 times 10 to the 5th, or 20,000 cubed. Which then becomes a very fun number of 0.000223215 radians per second. And I will include that many digits just because it is such a small number. And there you go. That's a good tool to guesstimate, I guess, where where you can expect to be in an orbit. Let's do one last thing, all right? Let's find out what our eccentric anomaly is going to be when we have had 6,000 seconds come by. What happens after 6,000 seconds? Where can we expect to be? So we rewrite our equation. A cubed by mu. Eccentric anomaly angle minus eccentricity times the sine, the eccentric anomaly angle. This is going to be a very short bonus example because this is about where it stops, at least for this portion. We're trying to solve for the eccentric anomaly angle. The problem with that is that we have an eccentric anomaly angle inside of a trig function and outside of a trig function. And that cannot be solved for the way that we have been solving it, right? So the three methods that are my go-tos for solving equations, there's the algebraic solving, which we cannot do, and I am so confident in that I'm not even going to try to do that. That's just going to be a huge mess. The other methods are like using a numerical method, using numerical methods. That can get you a reasonably accurate answer. The problem is that if you want to solve it in any amount of expediency at all, you have to use a computer for it. You do not want to mess with it by hand. And the third method is the graphical method, where you plot it out on a graph, and then, okay, here's the 6,000 mark. And look at the eccentric anomaly angle from there. The downside to that is that you're going to have a fair amount of errors associated with that. Just from, like, you have to make some interpolation there. So it will not be an exact number. And I think having shared all of that with you, I think this is a good enough time to wrap up the video. Hopefully it was a bit shorter than last week, and I hope you enjoyed. Thank you all so much for stopping by.